Hello, this is the group 14, and it's me, Abdulrazak Abdelkader, and I have with me today Omar Ahmed and Simko Kaduri, and I also have my friends Lizard and Ether. Sorry, I forgot the name. And what we have today is the lab 2, and here we start our lab. And we are using Jupyter Notebook as you give us opportunity to use. And here we have, we start first importing our necessary packages to be able to run this data set. And then we uploaded the data set file, as you see down there. And then as we presented our data, and then we have our data down below there, and then you have very clearly, you have every column, you can see the data column, you can see the temperature, you can see the humidity, you can see the light, you can see the CO2 and humidity ratio and occupants. And then if you go down, and then here we use describe our data, so we can see our data very clearly. And now I'm going to give my word to my friend Umar. He's gonna present the task 1.
So here, this is the task 1, and here we start. Here we perform a scatter plot with 2 specific columns as we choose, which was the temperature column from the data set and humidity ratio for the data set. And we presented, yes, and when it was in the column, of course, in the data set. And we presented in the as X value, the temperature, and as E value, the humidity ratio. And that is the plot shown here. And if you go down a little bit, on the 5, on the line 5, we see that here this is our correlation matrix, and it's showing the correlation. Here we transformed our data to the correlation matrix, and you see here like the different values of it, for example, yeah. And then if you go to the 6th line, here we then put our, we imported the Seaborn, we used the Seaborn library, then we use the heat map with the correlation data that we transformed. And in this heat map, you can see, for example, if you run it, yeah, you can see, for example, like the temperature. If you match the temperature with the temperature below, you see that the correlation indicates 1, which is a match. But if you see, like, for example, the black one, then you see like it's below 0.4, which means that it's no correlation at all. So, for example, between the temperature and the humidity columns, you see that is no correlation. So what we did here in the instruction is said like we needed to use 2 specific columns to match with each other. So by doing that, on the 7th line, here we forecast our correlation. Here we are inserting the forecast of the correlation data into our new variable, which is the forecasting underscore core. So if you run it, that line, you see that it works. And then on the 8th line, we did like we dropped, here we created a heat map for the forecasting underscore variable, and we dropped like the different columns that we didn't like needed. So for example, the CO2, the light, the opacity and humidity, and then yeah, the same goes for the other. And then we created a new variable which is named temp humidity ratio heat map, because we wanted to match the specific correlations between the temperature column and the humidity ratio. And we wanted to specify that in the heat map and just those 2 columns. And then you can see here, like, for example, -1, it indicates a perfectly negative linear correlation between the 2 variables. And 0 in the correlation matrix indicates no linear correlation between the 2 variables. And we can see that the 1 indicates a perfectly linear correlation between the 2 variables. So what we see in our heat map here is that if you compare like the temperature with a humidity ratio, you can see that it indicates 0, which means there's no correlation between the two variables. But when you compare the temperature variable with the temperature variable, which is a match, of course, and then you see that it indicates a perfectly positive linear correlation between the two. So, and yeah, and now I'm gonna give the word to my dear friend Simko, and he's gonna talk about task 2.
Yes, so for the task 2, we'll perform an Adfuller test to reveal the p-value and to check if the data is stationary or not. And to do that, firstly, we'll have to declare an array variables that will hold the carbon dioxide data, and we'll put it in the column of carbon dioxide in the data frame. And here, as you can see, we describe the data, which means that you will get a list out of all the important elements of what you can get out from a data. For example, the count of the data, the mean, the standard deviation, and so on and so forth. And by this, we can actually use this for different things. For example, if we have the number of observations, and that means the count, so to speak, and we'll use that to get the p-value also from all the carbon dioxide, because we have a formula for that. So what we do is firstly we'll use the result of the carbon dioxide, which is presented in a variable here. And the carbon dioxide results will give us the Adfuller results. By firstly, we'll do a new list, so to speak, which will present us with the test stats, the p-value, the lags used, and the number of observations. And to get that, we'll have to use for value a for loop that will say for every value in the zip of result of carbon dioxide with labels of carbon dioxide, print the label plus the string of that value. And we'll get the p-value out by using the Adfuller test function in this case, and we'll get the p-value from that. So, and not only will we get the p-value, we will also get the same count, almost the same count. This is not as exact, but as you can see, 9,717, 9,717, 9,752 is very close. It's not the same because when you do use the describe method, it will show you a bit more exact maybe. And when you use this for loop to count, it will be a bit different. But as you can see, it's quite similar, and the p-value will get out from this using the test stats. So since the data set provides us with the carbon dioxide values in different dates in the data set, you can see, for example, as Abdurrazak showed you, this is, for example, in 2015, the second month of the 18th of the second month, and this is the 11th of the second month, like in February, so to speak. So in that case, we can check the different values in different dates. So to do that, you will sort the data out from the date column, sorry, and we will create a new plot for that and index it to period in 1 minute. What's it called? 1 minute difference. So it will rise like 600, 800, 100, so in 200 for every data, and this is the dates for each data. And now we have demonstrated how you can take out the p-value, and also to demonstrate in the by the way, we were going to see if the data is stationary. And to see the data if it's stationary, we will say that if the result is well above 0.05, meaning it will mean that the data is stationary. And we can see that the data is well above 0.5. So the data is stationary. Okay, now I will give over the word to Mr. Zinho Zhu, is a lizard, and he will take the part where we the testing and training.
Yes,
So,
thank you very much. And I'm going to talking about the testing and training. And here we choose the train part is from all of the data from 0 to 2,500. And then we choose the test parts from 2,300 and 2,500. And here's model, we choose the ARMA. And the class within this model is a class statistical models for analyzing and forecasting time series data. And we think it's a generalization of simple autoregressives, like the moving average and add the notion of integration. And here you can see we use the model and use the chain data, and we use the weight function. And after the results, we can see all of the details of all of them. Our data shows like the everything, and after we got all of the data, and as you scroll down, and you can see, and you can use all of that. And we want to see the future data, so we use the forecast and predict that we from the 2,300 and use 100 data and as our predict result, and we put it into the Y practical, and also we use the Y test. We use the Y test. We hold the test value from the data, and it includes a filter. All of the results is working for the last final part, which will be introduced by my friend Ethan, and he will talk about all of this mean absolute error.
Okay, thank you. Now let me introduce the MAE part. MAE can better reflect the actual situation of prediction error. It can tell us how accurate the testing of forecasting is. MAE is the average of absolute error, and the calculation formula of FMAE is the average of absolute difference between predicted value and the actual value. We use ABS method to calculate absolute values, and then use mean method to calculate the average of all absolute values. Then we use round method to keep 3 decimal place for our MAE. And we can see our MAE is 18.988. Yeah, that's all of our presentation. Thank you for your listening.